Hi, this is Mark Weitzman. Welcome back to this deep dive, and this will be the final video in this series. And we're doing a deep dive on chi-squared and students' t-distributions. And independent of sample means and sample variances. And this is adapted from Matthews and Walker's text on mathematical physics, problem 14.7. And so previously we derived the PDF for the chi-squared distribution. We derived the independence of sampling means and variances. And we derived the PDF distribution of the sampling means and variances. So in this video, video 5, I want to derive the PDF of the student t-distribution. Now, the definition of the student t-distribution is Tn is n degrees of freedom is distributed according to a normal variable divided by a square root of a chi-squared n, chi-squared with n degrees of freedom divided by n. Now, I'll give an example of where we see this. So let's take a normally distributed variable like the sample mean. Remember, if x is distributed, x is normal with, say, mu comma sigma squared. Then x bar is distributed. X bar minus mu over sigma times the square root divided by the square root of n is distributed normally. So that meets this definition here. And we'll take a square root. And we showed in the previous video that s over sigma squared, I'm defining s as being a little unconventional, but it's just the sum of the squared means. So s over sigma squared, we showed that s over sigma squared over n minus 1 is distributed as a chi-squared. S over sigma squared is distributed as a chi-squared distributed as chi-squared with n minus 1 degrees of freedom So we're dividing by n minus 1. So this whole thing should be distributed as t n minus 1. And now I'm going to maneuver this. So this is equal to square root of n x bar minus mu divided by sigma divided by 1 over sigma times the square root of n minus 1 s tilde. Remember, s tilde is defined as s over n minus 1. So n minus 1 s tilde is just s. I took the sigma out, and then I still have the n minus 1 to divide by. Okay, and this is equal to the square root of n x bar minus mu divided by the square root of s tilde. This is equal to x bar minus mu divided by the square root of s tilde over n. So this is what we usually use for a t-test, and as I said, this is distributed according to t n minus 1. Okay, so let's find the distribution. Find the distribution of z divided by the square root of chi squared n over n. I'm not going to do the n minus 1 here. I'm going to do the student's tn. You can just substitute n minus 1 to n to get the tn minus 1. And here the distribution of z is, of course, we all know. And the distribution of chi squared n, which we did in the first video, is e to the minus chi squared over 2, chi squared to the n over 2 minus 1, divided by 2 to the n over 2, gamma of n over 2. Okay, and just to make it a little bit easier to write, I'm going to let w be distributed as chi squared n, so I can write w instead of chi squared here. And I'm going to define the variable tau is equal to z over the square root of w over n. So tau is a student's t variable. So first let's find. And I want to warn you, this is probably the most heavily mathematical of the these videos, and we're going to do some integrals and tricks. And I did not figure these out by myself. I'm stealing this from Schwamm's outline of probability and statistics. That I have from 40 years ago. I think I was studying for the second actuarial exam, so I used that book. So let's find the cumulative distribution of tau. Okay. So f of tau, by definition, is equal to the probability, total probability, that z over the square root of w over n is less than tau. Now we have two variables here, z and w, at the start. So this is a multiple integral, and we're just going to integrate over the whole range of values of z and w. The outside integral is w. W goes from 0, because it's a chi squared variable, it goes from 0 to infinity. I'll put dw here. And the inside integral, the the normal variable z, goes from minus infinity. But the maximum, since we're only doing z, can only go is less, z over this is less than that, z only goes up to tau times the square root of w over n. So this is a little tricky because the outside integral involves a variable, and that variable occurs in the limit of the integral of the inside integral. So I have e to the minus z squared over 2 over the square root of 2 pi. And then I have e, now I'm going from the chi squared, but I'm using w for chi squared. E to the minus w over 2, w to the n over 2 minus 1, and we're going to have a bunch of constant factors which are a pain in the neck to carry along, to the n over 2 gamma of n over 2. Okay, so let us, first thing we're going to do, we're going to define a new variable, y equals z over the square root w over n. I guess in a sense we're going back to our student t variable. So the outside integral won't change, but the inside integral will make substitutions. So f of tau is equal to the integral from 0 to infinity and then we're going to have the integral from minus infinity. Now here, okay, I left off the dz here. Here, when z equals tau over the square root of w over n, the square roots cancel, and so y just becomes tau. So the integral from minus infinity to tau, the dw is going to be for the outside integral. The inside integral, instead of being dz, is now going to be dy. Since z is y times the square root of n, dz is dy times the square root of w over n. Don't forget that measure factor. The integral from minus infinity to tau, e, now z squared over 2 becomes minus y squared w over 2n. I still have the e to the minus w over 2, and I have w to the n over 2 minus 1. Then I have all these constant factors that I have to drag along. 2 pi, 2 to the n over 2, gamma of n over 2. Okay, now here comes the, we've done this, here's the major trick. We can differentiate this with respect to tau to get the PDF distribution. F of tau is equal to dd tau of big F of tau. This is equal to, notice tau only occurs in one spot here in the inside integral. When you take a derivative of an integral with a limit like that, you just, wherever that integral is, notice it's like this. We substitute for tau for y. So this is just equal to the integral from 0 to infinity e to the minus tau squared w over 2n w. Okay, I left out. Well, I'll put the e back. W to the n over 2 minus 1 square root of w over n. I left out the e to the minus w over 2 dw. Then our constants. Okay, now we need to make one more variable change. Notice that the variable w, e to the minus w over 2, it just factors out. I'll write this out. The integral from 0 to infinity e to the minus w over 2 times 1 plus tau squared over n w. Notice there's a w here, so I'm going to write this as n plus 1 over 2 w to the okay, let me look at this. Okay, so I have n over 2 minus 1 here, and then I have a minus 1/2. So now this becomes n minus 1. So n over 2 minus 1 plus 1/2. So it becomes n minus 1/2. So this becomes w to the n minus 1 over 2 dw. And then there's our usual constants, but we also have the square root of n there. So I'm going to write this in a funny way and put that n with the square root of pi there, then take the square root of 2 out, 2 to the n over 2 gamma of n over 2. Okay, so this suggests the obvious substitution: u equal w over 2 times 1 plus tau squared over n. And so now we get f of tau is equal to, I'm going to take out all the, I'm going to take out some of the constants. 1 square root of pi n square root of 2, 2 to the n over 2 gamma of n over 2. Now I'm going to make this substitution, the integral from 0 to infinity e to the minus u. W is 2u divided by 1 plus tau squared over n. I'm going to raise this to the power n minus 1 over 2. Then dw is 2 du over 1 plus tau squared over n. Okay, we're almost at the end. So this is equal to, now it's just a matter of getting the constants out. 1 over the square root of pi n square root of 2, 2 to the n over 2 gamma of n over 2. Now here's 2 raised to the n minus 1 over 2, 2 to the n minus 1 over 2. I have another 2. And now I have the important factors for the distribution. 1 plus tau squared over n. This is raised to the n minus I know it's in the denominator, but first n minus 1 over 2, and then I have another plus 1, so this becomes n plus 1 over 2, and it's in the denominator. And I have the integral from 0 to infinity, e to the minus u to the n plus 1 over 2 minus 1. Right? N over 2 plus 1, so it's n minus 1 over 2. Okay. Now, all these 2's cancel. You can verify it yourself, but we have 2 to the n over 2. That cancels. That cancels. I have 2 to the minus 1/2. That's like a 1 over square root of 2 times the square root of 2 is 1/2, and then there's a 2 there. That cancels. That cancels. So all the 2's go away. So this is equal to 1 over the square root of pi n, 1 over 1 plus tau squared over n to the n plus 1 over 2. And then this is just our gamma function again. Gamma of n plus 1 over 2 equals another factor, gamma of n over 2. So this is the famous student's t-distribution for n degrees of freedom. And the main thing to notice is that because of this factor over here, there's very fat tails. And when n is large, it's suppressed and everything, but when n is small, those tails come into effect, and we can no longer use the normal distribution. The Gaussian distribution won't be a good approximation. So thank you very much for watching. This ends the deep dive on these distributions, and I hope that you might have gotten something out of these videos. I think videos 2 and 3, where we showed the essentially proved Cochran theorem, are the essential ones. The other ones tend to involve more mathematics. Thank you very much.